Okay, so let us continue with the diffusion flame regimes, that is which is the controlling aspect of a diffusion flame, for which we actually go for defining what is called flame fruit number. Okay, so this is a ratio of the initial jet momentum to the buoyant force experienced by the flame. Okay, so if you take, see, for example, what is buoyant force? If you take say hot wall, okay, a wall which is hot, TH, and the ambient is a T infinity, which is colder, so that is TH is greater than T infinity, then you can see that there will be a natural convective flow which is generated adjacent to the wall. Very close to the wall, you will see a natural convective flow. So similar to this, flame is a hot surface, and so that will lead to low densities for the fluid, which is the burnt product of combustion, and so they will rise up. So the acceleration of the hot products basically will cause the buoyant force. Okay, so the entire length of the flame will be experiencing that basically wherever it is hot and so on. So that is due to the density gradient basically. Okay, so you can see that the initial jet momentum is actually affected by the jet exit velocity. So if you increase the velocity, the momentum will increase. Buoyant force, as I told you, the entire flame length will affect it. Okay, so the acceleration due to buoyant force basically depends on the g value. So acceleration due to gravity, which is 9.81 meter per second square, and see, for example, if you take say Grashof number, say this is so g beta, then delta t, sorry, g beta delta t, then any characteristic length, so length divided by the nu square, length cube by nu square. So that is the Grashof number. So this is the number, non-dimensional number, which will control the natural convection, so the buoyancy force. So for example, if you take this g into L, then L square. So we can say g root of GL, that will be the velocity term, root of GL. Okay, so this so if you take a root of Grashof number, basically put GL and L square. So this L cube can be written as L square into L, and G into L can be written here. So this if you take this root of GL, that will be the velocity term. So this will be the natural convective velocity, velocity due to natural convection. So you can see the units also, meter per second square into meter under root, so it will be meter per second. So this is the velocity which is actually induced. So this root of GL will be the natural convective velocity, the average magnitude of the natural convective velocity. So this acceleration depends upon the acceleration due to gravity. So it's generally we can use the acceleration induced due to buoyant force as 0.6 g into, it is some factor, some scaling factor, it's approximate, please see that, into Tf, that is the flame temperature, minus the ambient temperature. So this actually is the delta T. So this is delta T which you are talking about, this delta T, and divided by T infinity. So this 1 by T infinity is like beta. Okay, so this particular term will be the acceleration term basically for us. So this flame acceleration, this is due to the density gradient. So from the flame to the ambient, the density gradient, because temperature and density is this inversely proportional to the density. So the density gradient is actually represented here. So the fruit number is written as to represent the jet momentum, V square term comes here, to represent the buoyancy force, A into LF comes here. So this is the fruit number. So this flame fruit number defined like this can be used to determine which is controlling the jet flame. So for example, if you take a fruit number much higher than 1, so that means either V square is very high, or the acceleration due to buoyancy force, or the buoyancy force itself is very low. So the flame is momentum controlled by the momentum of the jet itself. Okay. On the other hand, the other extreme case, if fruit number is much less than 1, then the flame is buoyancy control. So you can see that if it is less than 1, V square will be very low, or the buoyancy force will be very high. In both the cases, you can see that it will be buoyancy controlled regime. If you have the fluid momentum order of 1, then both jet momentum as well as the buoyancy force both will control this. So, as I told you in these figures, you can see these are all figures, photographs which show the jet diffusion flame at several flow rates under normal gravity. So, under normal gravity condition, you get these flames. So, if you actually try to reduce the gravity or try to do experiments in space or microgravity, etc., the flame shape will be entirely different, flame length will be different, and so on. Okay. So, that is the important thing you should understand. So, which is going to control which force, whether it is momentum control or buoyancy control, or both are important. So, you have to understand that. So, based upon that, theoretical correlations are developed. So, let us see some flame height correlations. We will see only empirical correlations here. So, Roper was the researcher who proposed several correlations for flame height. Okay. So, based upon experimental results, so that is called empirical correlations, and I have given this correlation basically used for circular cross sectional ports, and we have considered only the laminar regime here. So, in the laminar regime, considering circular ports for several fuels, the Roper's correlation for flame height is given here. That is, the length of the flame or the flame height will be equal to 1330 time QF is the volumetric flow rate of the fuel. Okay, QF is the volumetric flow rate of the fuel given here, and T infinity is the temperature of the oxidizer stream, and T capital F suffix capital F is the fuel stream's temperature, and S which is appearing in the bottom in a natural logarithm term is the molar stoichiometric oxidizer fuel ratio, molar based. Please understand, when I say air fuel ratio or oxidizer fuel ratio, in general we write it in terms of mass of the oxidizer divided by the mass of the fuel, but specifically S which is used in the correlation is molar. So, that is number of moles of oxidizer divided by the number of moles of fuel. Okay. So, considering stoichiometric combustion. So, stoichiometric combustion, because in the diffusion flames, the flame zone is formed because they are separately, the fuel and oxygen are separately supplied to the combustion chamber. So, based upon the locations where the stoichiometric mixing takes place, the flame zone is formed there. So, stoichiometric oxidizer to fuel ratio is considered here. So, number of moles of oxidizer divided by number of moles of fuel, that is S. Okay. So, this correlation clearly mentions that the LF is directly proportional to the flow rate, which we have already seen by the scaling analysis. The scaling analysis, what we saw by considering the time it takes to reach from the central the axis to the radial location of the flame, or by diffusion, or the time taken by the molecule from the base of the flame to the tip of the flame by convection. Both should be same. By equating that, we found that the length of the flame or the flame height depends on the volumetric flow rate. So, that is what is correlated here basically, that is very important, and please understand here we require the temperatures of the oxidizer and fuel stream, and also the stoichiometric molar stoichiometric oxidizer to fuel ratio. So, this LF has been correlated for several fuels. Experimental results have been used to arrive at this empirical correlation. Okay. So, as we have seen already, the volumetric flow rate is very important. So, when you increase the flow rate, the fuel typically takes more distance to find its oxidizer and completely oxidize. Okay. Other than that, we can see the type of fuel, because the S will depend on the type of fuel. Then the diluents added. See, for example, in the experiments what we try to do in a jet diffusion experiments, only fuel is supplied from the port. But if you see, all other phenomena are naturally occurring. For example, the air entry to the flame is by natural entrainment. Then mixing is basically dependent on the radial diffusion and so on. So, but in several cases we need to control the flame, for which we normally try to add diluents like say nitrogen, okay, to the flame, even CO2 in some cases and so on. So, some diluents are added, okay, or if you can add some amount of air to the fuel stream. But please understand that we are not completely pre-mixing the fuel. We will add some amount of air. So, that may be not in the limits also, the flammability limits also. When you add something in the fuel stream, that is called primary air. So, why we do this? Because to have better control of the flame. We will see about that little bit later, but we have to understand that there are scenarios in which we will be able to add diluents like nitrogen, carbon dioxide, etc. to the fuel side. Similarly, some amount of air can be added to the fuel side, which is called primary air. So, if you do those things, these are the parameters which are going to affect the flame length. So, in those cases, how this correlation can be used, that we will see. So, basic type of fuel, okay. So, basically when I say type of fuel, I will say if it is hydrocarbon, I will say the H/C ratio for an hydrocarbon. So, something like that. So, these are all very important things which will affect the length of the flame. So, we will see about this. So, once we change the fuel type, etc., S itself will change basically, and based upon that the flame length will be affected. Okay. So, we will see how to modify this correlation and use it for several purposes. Let us first see, for a given hydrocarbon fuel, Cx and Hy. X is the number of atoms of carbon and Y is the number of atoms of hydrogen. The molar stoichiometric fuel ratio S is given by this. Okay, so that is X plus Y by 4. That is the number of moles of oxygen required in the stoichiometric equation, divided by the mole fraction of oxygen. Okay. So, this is when you take standard air, you have XO2 will be equal to 0.21. Okay. So, this you can also do another way also. See, for example, if you have a equation say CH4 plus 2 times O2 plus 3.76 times N2 giving CO2 plus 2 H2O plus 2 into 3.76 times N2. So, this is the stoichiometric equation. So, what we can do is S can be calculated as number of moles of oxygen, that is 2 into 4.76 divided by number of moles of fuel, which is 1. So, this is also correct. So, if you do this, or you can do the way what we have given here, 1 plus 4 by 4 by 0.21. So, that is the for the standard air, that is the mole fraction of oxygen is 0.21, 79% of nitrogen, 21% of oxygen by volume. So, the mole fraction is this. So, you can use this to get the value of S. So, now seeing this scenario, say X plus Y by 4 and this, you can see that the flame length increases as H/C ratio of the fuel decreases. So, H/C will if it decreases, for example, this is the case CH4. So, let us say C2H2, okay, then you can calculate the H/C. So, basically physically what we should understand here is, if H/C ratio decreases, then the flame length increases, okay, when H/C ratio of the fuel decreases. So, why it is? Because if you take hydrogen 1 mole of hydrogen will require only half mole of oxygen. So, when the H/C decreases, then your oxygen requirement will increase, because carbon requires 1 mole of, say, carbon plus O2 gives CO2 for complete combustion. So, you can say 1 mole, here only half mole is required. So, when H/C ratio decreases, you can see that the oxygen amount will increase, that means the S value will increase, correct. So, S value will increase. So, that is the reason. So, and also the reactivity of the fuel will reduce. When H by C fuel of the fuel decreases, the reactivity of the fuel will reduce, so it may take higher length to completely burn. That is also another reason. So we can use this and solve. Okay, so now if you see this correlation, 1 plus 1 by S appears. So here if S increases, then this denominator 1 by S will be higher, 1 by S will be lower. So this term will be lower, the ln of this will be lower, so the flame length increases. So mathematically also we can see like that. Okay, now coming to the mole fraction of the oxygen. So I need not always use a standard air. I can enrich the air with some more oxygen. For example, what will happen if you increase the mole fraction of oxygen from 0.21 say to 0.3 or 0.35, something like that, then you can see that when you increase the mole fraction of oxygen, there is a tremendous decrease in the flame length. Or other way, if you decrease the mole fraction of oxygen, okay, so for example, I dilute the oxygen stream with say with some products of combustion. See, this is normally done to reduce the NO formation. Say in the standard air, I will try to mix some products of combustion like CO2, H2O, etc. So when you dilute that, okay, it's called this recirculation of the burn gases, correct? Combustion gas recirculation. If you do that, then what happens is the mole fraction, the effective mole fraction of oxygen in the air stream, it will come down. That will increase the flame length. That will cause notable increase in the flame length. On the other hand, as I told before, if you increase the carbon, enrich the combustion, I want to get more higher temperature, and so I increase the oxygen content, mole fraction from 0.21 to say 0.3, then there is a reduction. Okay, so we can see that for a methane fuel, if I use pure oxygen, that is XO2, here XO2 equal to 1. It's a pure oxygen if I take, then you can see the flame length is reduced to about 1/4 of the value, okay, for a given flow rate. Obviously 1/4 of the value that was observed in the air environment. That is, air environment is XO2 equal to 0.21. When I use XO2 equal to 0.21, that is standard air, I get a flame length say LF1 for a given flow rate QF1, and keeping the same QF1, but I go to a pure oxygen environment now, inject this in a pure oxygen environment. For the same flow rate, the reactivity increases very much, and you can see that the flame length reduces by 1/4 of the value, that is LF1 by 4. So these are something we should understand. When the H by C ratio of fuel decreases, the reactivity decreases because hydrogen is reduced. The oxygen required will increase, so that the flame length increases. Then mole fraction of the oxygen, when the mole fraction of the oxygen increases, then the flame length decreases. That is what here, pure oxygen 1/4 you can get. So a small reduction of oxygen mole fraction in the air will cause a notable increase. So that is another important thing we should understand. So these are the things which will have the factors which affect the flame height. Okay. So now we go for dilution. Okay. So as I told you, in the fuel stream, fuel plus I can add some nitrogen or some CO2, etc. Even when you use say heavy fuels, we can also add some steam with this. So that so a lot of things we are doing. For example, when I add some nitrogen or say water vapor, etc., we see that the soot formation decreases. The soot formation of, if a sooty fuel, let us take this is say C2H4 or something like that. If we add some water vapor to this or nitrogen to this stream, a little bit, not too much, then we see that there is a decrease in the soot formation. However, what happens to the flame height in that case? So when the fuel stream is diluted with an inert gas, okay, such as nitrogen or as I told you other gases, then yes, we have to recalculate by using this expression where S is equal to X plus Y by 4, same, but denominator you can see, instead of just XO2, I have 1 by 1 minus X diluent into XO2, where the mole fraction of the diluent is nothing but X suffix DIL. So when you can do this. So now what happens if you do this? If I increase the mole fraction of the diluent, the flame length decreases because the fuel component comes down basically. So, the flame will find the fuel will find enough oxygen within a shorter length. So, the heat release etc. will come down, but anyway the flame length will decrease obviously because of the decrease in the fuel content. Okay. Now, on the other hand, when I told you again for the same purpose of reducing the emissions, improving the combustion efficiency by completely burning CO etc., we normally add some primary air to the fuel. So, it may be said it is actually counted in percentage of the stoichiometric air. So, if stoichiometric air is 100%, I say I will supply about 10%, 20%. So, normally I keep this mixture of fuel and primary air to a limit where it will be outside the reach limit of the premixed flame. So, that is what we will try to keep. If XPRI is the fraction of the stoichiometric air supplied as primary air, please understand it is not mole fraction. So, if the number of if the quantity of air supplied is say stoichiometric air is say some volumetric flow rate say let us say 100 LPM is the stoichiometric air requirement, then Xp can be 10% of that, say 10 LPM. So, Xp is actually the percentage of stoichiometric air. So, in some fraction, so it is fraction, so it may be 0.1, say I can say 0.1, 0.2 etc. for 10%, 20% and so on. Okay. So, now so please understand the Xp is nothing but the fraction of the stoichiometric air supplied as the primary air along with the fuel. Okay, in that case, how will I calculate the S? So, S will be calculated using this Xp plus I will also use the S fuel term, which is the value of S when the fuel alone is supplied, that is S fuel will be equal to X plus Y by 4 by X of O2. So, please understand this X of O2 is the oxygen mole fraction in the air stream, but this Xp is the fraction of the stoichiometric air which is supplied along with the fuel. So, that we have to understand. So, this is calculated, then this is substituted here. So, other than that we have 1 minus Xp, which is the fraction of the fuel basically divided by Xp plus 1 by S fuel, which is calculated like this. Okay. So, you can see that when you supply primary air, there is a clear reduction in the, there will be a clear reduction in the flame height. Okay. So, if S is modified, please understand this correlation basically in this robust correlation, this S can take up several other factors. For example, the fuel type itself, S will vary with fuel type. Then if you add any diluents, the S can be modified accordingly. Then when you add primary air, S can be modified accordingly and recalculated and substituted. So, other than that, we have only simple terms like the oxygen temperature, which we can easily measure, fuel stream temperature also easily measurable. There is no other gas required like flame temperature etc. are not used. Then volumetric flow rate anyway we will measure. This is for the fuel stream, okay, that we will measure. So, if you know this and calculate S accordingly for any scenario, you can calculate the flame length, and this actually comes out nicely for several cases. Okay. So, you can see that when primary air is added, then also we will see there is a reduction in the flame height, that we will demonstrate it when we go ahead. Okay. Now, Roper's correlation for circular ports have been seen. Now, Roper has also proposed correlation for square ports where this type of correlation is proposed. Okay. Again, it is empirical correlation, experimental based correlation results are used to correlate this. Similar terms are seen here, some constant, volumetric flow rate. So, LF depends directly on volumetric flow rate. Again, the temperature of oxidation stream, temperature of the fuel stream are incorporated. However, instead of there in the circular things, natural logarithm of here 1 natural logarithm of 1 plus 1 by S was used. So, but here the function for S in the denominator is different. So, here what is used is the inverse function of the error, inverse of the error function is used. inverse of error function, that is that of 1 plus s 1 by 1 plus s under root, okay, total square. So, the denominator is total squared. Okay. So, this error function, basically error function ERF is tabulated from standard tables. We can get this standard tables, you can get the error functions for every value. So, for example, calculate this 1 by root of 1 plus s. So, you will have one value. For that you can find the error function. Once you find the error function, inverse of the error function can be found by applying this. So, you know this value, and from this value you can take this. So, it is only the inverse of that. So, from the error function table itself we can recalculate the inverse function, inverse error function. So, once you do this, substitute that to get the flame length. So, the functional dependent of S, okay, on the denominator. Say, okay, for example, here LF, the functional dependent on LF on S is different, that is it. So, if we have used natural logarithm for the circular ports, here inverse error function based functions for the S calculating, the S calculation is same. Again S for a normal oxidizer is calculated using x plus y by 4 by mole fraction of oxidizer. If you have diluents, you have to modify that. So, these correlations, the calculation procedure for S is the same, but the way S is used in a function, that is different for the square ports. Okay. Similarly, correlations for slot burners are given. So, for example, in the whatever we have seen, so circular and square ports, you will see that the correlation will obey both momentum and buoyancy control regimes in both circular and this. However, for slot burners, okay, separate correlations are given for momentum and buoyancy control regimes. So, separate correlations are given for momentum. So, again Froude number for the flame is calculated, and based upon the Froude number, separate correlations are attempted or are proposed for momentum and buoyancy control regimes. So, these are very useful correlations to calculate. So, why we need this? Because we have a combustion chamber. To calculate the dimensions of combustion chamber, we need to understand what will be the length of the flame. So, if for example, if you want to target this flame on a particular wall or any object to heat the object, then you need the flame length calculations. Even in domestic stoves, okay, so we need some height of the flames coming out of individual ports. It's multi-port stove, correct? You can, in a normal domestic stove, you can see that multiple holes will be there, and the flame height coming out of these holes will be restricted to some quantity, say 20 mm, 15 mm, something like that. So, it cannot be very high, correct? So, to calculate this and design your burners, burner port diameters, etc., the flame height correlations are extremely useful. So, that is what is given here by Roper's correlations are very famous, and based several other correlations also are available. So, Roper correlations are very famous, very simplistic in nature, because you can see that the dependency on the QF is brought in, a dependency on the type of fuel, whether diluents are added or not, or whether primary aeration is given, okay, partially premixing, everything is taken into account by this. Yes, then we also use the oxygen, oxidizer stream temperature, fuel stream temperature, and so on. So, in this case, all the factors are built into this correlation in a simplistic way.